Find any asymptotes and the coordinates of any removable discontinuities for each rational function. So in the first one, we have f of x. Notice we're dividing by x squared minus 4. So we need to think about what values are restricted from the domain. Well, we can see that x squared minus 4 will factor to x plus 2 times x minus 2. So we're going to come back and look at that in just a minute. If we look at the graph, notice that if put parentheses around the entire numerator and denominator again, and if I zoom 6 it just to get the standard window, okay, it looks like there's a vertical asymptote over here on the left side. So let's look at what happens. We notice that when we simplify your rational function, factor the denominator by difference of perfect squares, and you end up with 1 over x plus 2. So notice that the x minus 2 is a common factor. So what that's going to tell us is that at x equals 2, we're going to have a removable discontinuity. The negative 2 value that's left over for x, that'll give you 0 in the denominator, that'll give you the vertical asymptote. Okay, so if you sketch a graph of that function, and again, we can look at the calculator where the removable discontinuity doesn't show up, but if I press trace and I put in positive 2, notice nothing will show up. If I put numbers that are close to 2, like 1.999, that gives me very close to 0.25 or 1/4. So if you were to put in our function right here, 1 over x plus 2, if you put 2 into that function after you remove that common factor, put 2 in, you get 1 over 2 plus 2, which is 1/4. So that's where the coordinates of the removable discontinuity would be, is at 2, 1/4. Okay, so we sketched the graph, and then just label all the asymptotes. Now I call the removable discontinuity a hole on this one. Same idea. Okay, the horizontal asymptote is at y equals 0, because when you put large numbers in, positive and negative, then you end up going to 0. So when you look at the equation, if you put large numbers in for x, the denominator gets much larger than the numerator does. So you have a smaller number divided by a much larger number, which goes to 0. Okay, so if you pause the video and try part B, and I'll put the answer up. Okay, notice that one will factor to x times x squared minus 16 in the numerator, and that does factor again with difference of perfect squares. The bottom, the denominator, is not difference of perfect squares. Okay, so because once you factor the x out, you're just left with x minus 4, so you gotta be careful with that. So we notice that the x will reduce out, and the x minus 4 reduces out. So that tells you when x equals 0 and positive 4, you have a removable discontinuity in your graph. Okay, so if you sketch a graph, notice that this whole thing just turns out being a line with 2 holes in it. Okay, so when x equals 0 and when x equals 4. Okay, so there's the asymptotes. There are no vertical or horizontal asymptotes, and you have 2 removable discontinuities at 0, 4, and 4, 8. So if you plugged in 0 and 4 in for x, that gives you the 4 and 8 for the y values for the holes. Okay, and then if you do the bottom of the page, I'll show you the answers. So you can do these and figure out what happens in them. Okay, so there's number 6A. Okay, so nothing cancels out on this one. Okay, so nothing reduces out. So what happens here is we have two x-intercepts at negative 2 and 2. That's when the numerator equals 0. And then when x equals 0, our function is undefined. We have a vertical asymptote, or an infinite discontinuity, at x equals 0. Okay, the horizontal asymptote here is at y equals 1/5. And if you pay attention to what's happening there, when you put large numbers in for x, what happens is x squared and x squared go to the same number. So for example, if you put 10 in, that's going to be 10 squared or 100, and then 10 squared in the denominator is 100. So they would reduce out, and you're just left with the 1 over 5. Okay, so what happens there? You get a horizontal asymptote at 1/5. Okay, and again, to find the x-intercept, that's where you set the function equal to 0. Basically, the numerator equals 0. You just have to make sure that nothing canceled out. If something canceled out, it can't be an x-intercept. So just make sure that you remove any common factors first to get the removable discontinuities, and then set the numerator equal to 0, and that'll find the x-intercepts. And then here's the last one. Okay, again, on this one, nothing cancels out. So there's no removable discontinuities or no holes in the graph. So in the denominator, set that equal to 0. You get negative 1/2 and positive 3 for the x values of the asymptotes. The x-intercept, you let the numerator equal 0 and solve it to get 7/4. And the y-intercept, you put 0 in for x. Okay, and here, the horizontal asymptote is y equals 0. And this is a good example because this is one that shows you that when you look at horizontal asymptotes, you're looking at end behavior. You can cross a horizontal asymptote generally if you're near the origin. You may cross a horizontal asymptote because what you're looking at with a horizontal asymptote is the end behavior of the graph. So as x gets really large, what's happening is the denominator, the x squared term, is getting much larger than the x to the first term in the numerator. So you have a much smaller number divided by a larger number goes to 0.